Next, let's consider this integral on this curve. Now, the integral is just as it's written. The curve is just the arc of the x squared plus y squared equals 1 function plus the segment of the x-axis from x equals -1 to x equals +1. This forms a nice closed curve, and Green's theorem should apply. Now, to perform this integral, we're going to parameterize the curve as C1 plus C2, where C1 is just the arc and C2 is the straight line segment. So the arc, again, is x squared plus y squared equals 1. This suggests that we parameterize using the Pythagorean identity that the cosine squared plus the sine squared of the same angle has to equal 1. So we let x equal the cosine of an angle, let y equal the sine of an angle, and let the angle go from 0 to pi, so that x equals cosine of, well, we have some options here, but the option we're going to use is x equals cosine of pi t, y equals sine of pi t, where t goes from 0 to 1. Pi t then goes from 0 to pi, so that x will go from 1 to -1. And sine of pi t, well, pi t goes from 0 to pi, so that the sine goes from 0 up to 1, back down to -1. And this, which should be a familiar parameterization by this point of the course, gives us a nice parameterization of this arc. Now, we don't have to use the interval from 0 to 1. We could have done cosine of t, sine of t, and let t go from 0 to pi. I chose to let x equal cosine of pi t, y equals sine of pi t, just for the convenience of t running from 0 to 1, but there are advantages to just doing the cosine of t and the sine of t. That's totally a choice that you can make arbitrarily in a case like this. Okay, C2, we're just going to let x equal t and let t go from -1 to 1. X goes from -1 to 1, and y remains 0. So the parameterization of this part of the curve is very straightforward. Now, we observe that on the C2 part of the curve, y equals 0, so that negative yx squared is going to equal 0, and xy squared is going to equal 0. So this entire integrand is going to be identically 0, meaning that the integral over C2 will be 0. So we don't have to bother integrating over C2. It doesn't contribute anything to the integral around the boundary. On C1, negative yx squared dx plus xy squared dy equals what? Well, y is the sine of pi t. We have the negative. X is the cosine of pi t, so we have the cosine squared of pi t. And then we have dx, which is the differential of cosine of pi t. The xy squared dy term is similarly obtained. X is cosine of pi t. Y is the sine of pi t. Y is squared, so that's going to be squared. And our dy becomes the differential of sine of pi t. Now we've got to be a little bit careful taking our derivatives. The differential of cosine of pi t is what? Well, it's going to be chain rule negative pi times the sine of pi t. Now that would be the derivative with respect to t of the cosine of pi t. The differential we multiply by dt essentially, so that the differential is going to be the derivative with respect to t times the dt, just this times dt. And then the cosine of pi t times the sine squared of pi t, etc. Write this, and that's plus, not equal. I have to fix that in a minute, so I'll kind of put my finger over that. So we have plus cosine of pi t here. We're going to get a pi cosine of pi t here. Let's write it out. Cosine pi t sine squared of pi t times pi cosine of pi t dt. Make sure we've got all that on the screen. If we write all this out now, we find that we have what? We have the factor of pi dt throughout. So we're going to put the pi out in front. And then what do we have? We have a negative sine of pi t and a negative sine of pi t, which gives us sine squared of pi t. And we have a cosine squared of pi t. So that gives us sine squared of pi t, cosine squared of pi t. And let's go ahead and make sure we have all our parentheses. And over here we get the same thing. We don't have any negatives. We have a cosine squared and a sine squared. So we have then plus sine squared of pi t, cosine squared of pi t dt. Okay, these two steps are going to magically appear before you. I didn't have the recorder on when I thought I did, but it's fairly straightforward to get from here to here. We have a sine and a sine, both negative, so we have a sine squared, we have a cosine squared. The negatives give us a positive, and we bring the pi out in front because both this term and this term contain that factor of pi. We factor the dt out, which occurs in both terms, and we easily see that this term multiplies out to a cosine squared and a sine squared, the same as the other, so that we can write the integral. Okay, so our original integral over c now becomes the integral from t equals 0 to 1, because that's how we parameterize the curve. We factor out the 2 pi. We get a 2 because we have the sine squared, cosine squared twice. So we have 2 times the integral from 0 to 1 of sine squared pi t, cosine squared pi t dt. Now I'm not going to complete the evaluation of this integral. I'm not going to go through all the integration technique. It's easy to integrate this, integration by parts. Integration by parts can lead you to a reduction formula, trigonometric substitutions, sum of angles, difference of angle formulas, and so forth, double angle formulas, half angle formulas, that sort of thing can be used to simplify the integral and put it into a form that's easily integrated. What we really want to see is that this integral, which is the integral over the curve, should then equal the integral over the interior of this region, the area integral of negative mx plus ny. Now our m function is the function we've got in front of the dx. It's negative yx squared. It's negative yx squared. And n is the coefficient of our dy. That's our xy squared. So that my equals negative x squared and nx equals y squared. Why do we want to find my and nx? Well, because Green's theorem tells us that this integral has to be equal to this integral. Okay, the integral of m dx plus n dy is equal to the integral of, that should be negative my plus nx dA. So let me fix that. Okay, so that negative my is a negative of negative x squared, nx is y squared. We have the integral of x squared plus y squared dy dx. I've already written in the limits on the integral, but let's see where those come from. Here's our curve, and if x squared plus y squared equals 1, then y squared equals 1 minus x squared. So along the top of the circle, the part above the x-axis, the part that we're talking about here, y is equal then to plus the square root of 1 minus x squared. So if we have x coordinate here, the limits on the y values are from 0 to the square root of 1 minus x squared. Now x goes from negative 1 to 1, so our inequalities are 0 less than or equal to x less than or equal to 1. And then for given x, y goes from 0 to the square root of 1 minus x squared. And for this reason, the limits on our integral, x goes from, and I said from 0 to 1, it goes negative 1 to 1. So, x from negative 1 to 1, our x limit is negative 1 to 1. For given x, y goes from 0 to 1 minus x squared, 0 to 1 minus x squared, square root of 1 minus x squared. And seems like I've got inverse errors here. So this one should go from 0 to the square root of 1 minus x squared, this from 0 to the square root of 1 minus x squared. I'll fix that. If the region was the entire circle, then this would be the appropriate description, but our lower limit on the y is 0. Now the limits on the integrals match the limits on the inequalities. It's always a good idea to write these things down independently and then double check them. I just caught a rather serious error by doing that, and you can do the same. That doesn't justify my having made the error, but you can at least take a lesson. Now this integral is evaluated. Well, we integrate from negative 1 to 1. Our antiderivatives are x squared y plus y cubed over 3, integrating with respect to y, and that's evaluated between 0 and the square root of 1 minus x squared, and then with respect to x. Now from some of the integrals we did in chapter 12, we're going to end up talking and writing 0 at the same time. Okay, I've made that go away, and we'll replace that with negative 1. Now, substituting for y, we end up with x squared times the square root of 1 minus x squared plus square root of 1 minus x squared evaluated for y gives us, let's bring the 1/3 out, and then we're going to have 1 minus x squared to the 3/2 dx. Now at this point, I'm not going to continue the integration because, again, we're getting into techniques that'll bog us down here. I'm simply going to say that we could let x equal, let's say, sine theta, so that dx equals cosine theta d theta, and reduce these integrals to trigonometric integrals that we can then evaluate using the usual techniques. Our integral is just pi over 8, but of course we've got a lot of steps between here and here, and this integral you should also be able to verify is pi over 8. Now there's actually a way to see this if you understand the integral as the average value of a function multiplied by the interval. The average value of sine squared over any interval where the sign goes from 1 to negative 1 or from 0 to 1 is going to be 1/2. The average value of the cosine squared is going to be 1/2. More importantly, the average value of the sine times the cosine is going to be 1/2. Using that fact and a little bit of reasoning, we can figure out that this integral should end up being pi over 8. We should, well, let's not go into the details of that. One way or another, there's a symmetry argument that allows us to determine this without doing the actual integration, but we should do the actual integration here and here, and we do get the same thing. As before, we have two different integrals, and those two integrals in this case turn out, I think, to be about equally challenging. They both involve trigonometric functions. But again, you'll encounter examples where one integral or the other will be much easier. So if you need to find the more difficult integral, you can always evaluate the easier integral and verify that the conditions of Green's theorem hold so that you have the result for both integrals.